Hi everyone, Mr. Ang here. So this is part one on our chapter on waves. So waves actually has an additional chapter added onto it, which is also sound. Okay, so in the syllabus, you will see that they are actually part of the same topic, but inside the slides, they're considered different topics. However, the next chapter, chapter 10 on sound, is actually a very short chapter, so we'll be doing them together as well. So, how do we describe wave motion? We'll start with that. Okay, and the learning outcomes is to talk about wave motions using vibrations in ropes and springs, as well as demonstrations of waves in a ripple tank, and also the understanding that waves transfer energy without transferring matter. So, waves are actually often used to explain physical phenomena such as light and sound. And the definition of a wave generally is a disturbance that propagates through space that transfers energy but not matter. Okay, so you've already encountered some of this, especially in our earlier chapters, for example, when we spoke about energy and how energy can be transferred. Okay, there's mechanical waves and there's also other waves like electromagnetic waves. So one example of waves is water waves. So like ripples in a pond, okay, you have a lot of types of waves that we exist, okay, that we see exist around us in our day-to-day lives. However, okay, for the waves produced by ripples, they're not actually very equally spaced or very nice to study mathematically. So that's why we try to have a more controlled environment using regular waves by a wave generator, okay, which is driven by a motor. So here I'm going to show you two examples of such waves. So in my first video over here, okay, you'll see a ripple tank and you will see, okay, the ripples produced when the person taps on this ball, which will then agitate the water surface and produce ripples. So you can see that, okay, the waves on the surface are going to create shadows or distort light. We will learn about that later on in a further chapter about refraction, okay, and that actually creates that circular pattern. However, okay, for a very systematic way of looking at waves, okay, what we have over here is a different setup. So a motor is driving this, and again, you can see the waves traveling from right to left, okay, based on the way that it refracts light. So these are just two simple examples of waves in a ripple tank that are demonstrated, okay, different types of water waves. However, waves do not only exist in water, they can exist in all different types of media. So another example of waves would be rope waves. So for rope waves, okay, what we have is one end of a rope, for example, being fixed to a wall. For those of you who go to the gym, okay, you might recognize this as being very similar to the battle ropes. Okay, so what we have is the other end is moved repeatedly and regularly, so up and down. So you can see over here in the figure, the person's hand, you've got the arrows there, is supposed to move the end of the rope up and down, and the direction that the shape of the wave travels, okay, that is the direction of the wave. So in this case over here, that wave is traveling from left to right. So within this wave, okay, each particle's motion is perpendicular to the wave direction. So the rope is the medium through which the wave moves. Okay, the rope is what transmits the wave. And you will notice that, okay, very easily noticeable, the rope itself, okay, does not move along with the wave. It's not as if, okay, the rope is moving from left to right. When the person is moving their arms up and down, what is actually going to happen is you are going to see that, okay, individual particles inside the rope are moving up and down, but they are not actually moving from the left to the right. So if we use a wave generator instead of, okay, using your hands, so we get a more regular pattern. okay, what is going to happen is that because the particles within the rope or the sections of the rope are joined to each other, what is going to happen is as the end of the rope is moved up or down, the next section is going to feel a force from the previous section and then also move up or down. So you can see over here particles A and B in this diagram. Okay, they are going to move up and then down, and that is how the wave is going to propagate. So B is going to actually also end up pulling the next particle, which is not illustrated in this diagram, up. So over time, you will see that this shape will move from left to right. So the direction of the wave is from left to right, whereas the direction of the vibration of the particles is up and down. So this is what we call a transverse wave. Okay, and here's another example which makes it even more clear. So what we have here is the Kallang wave. Okay, so you can see over here, this is the Kallang wave. This is very clear example of a wave you saw just now through the video. Okay, that people were standing up or at least raising their hands up and waving the Singapore flag. So this was, I think, the first National Day parade at the new National Stadium in 2016. And you could see that this wave was moving through the stadium. Okay, however, the people were not moving along with the wave. The people that make up the wave, they are like the particles in the wave or the medium, okay, that transmits the wave. Everyone was just moving up and down, standing up or raising their hand, and not actually moving from left to right, okay, through the entire stadium itself. So this is a very clear, nice example, okay, because sometimes in, for example, a water wave, it's very difficult for us to pinpoint any particular molecule or particle or water. So using this example of people makes it very, very obvious and very visible that in a wave, okay, the motion occurs without the individual particles of the medium or the individual people, in this case, moving in that direction of the wave and being transported along the wave. So, like I said earlier, the segments, okay, A and B, as well as all the subsequent segments, they do not move along the rope. There is no transfer of matter. And for any given segment of the rope or for any given person participating in the Kallang wave, the motion can be described as periodic or cyclical because it repeats. Okay, of course, the Kallang wave doesn't go on forever, but you saw that it went around the stadium at least once. So if that wave had gone on a few rounds, okay, it's a repeated motion. You stand up, you wave your flag, you sit down, and then the next time the wave comes around, you do the same thing. Okay, so it's periodic. Every however many seconds, the motion will repeat itself. So that is why we describe it as periodic, and later you will see one of the properties of the wave is the period, which is the time it takes for the motion to repeat. So you can see therefore that a wave is a disturbance, okay, that propagates through space and transfer energy but not matter. So in a way you can say it's a disturbance because the rope or the people are moved from the original position. And then when they are moved from this original equilibrium position, okay, they transfer energy along. But the particles itself in the long term do not travel with the wave. So another type of wave, okay, is a wave in a spring. Okay, these are called longitudinal waves. So this you might be familiar with slinkies. Okay, so this wave in a spring, okay, can be created instead of moving the slinky like a rope up and down. We can actually push or pull the end of the slinky. And when you do that, okay, a different type of wave is formed. And you can see over here that you will have compressions along this spring. And the wave, of course, would travel along the spring. So in this case, also left to right. Okay, but the particles themselves, say for example, loop A, B, and C, they aren't traveling up or down. They're actually traveling left and right. So here I have another example of a wave on a slinky coil. I'm going to skip to the relevant part. Each little wire of the slinky representing an air molecule. What I'm going to do is start vibrating one end of the slinky, and you can see that the one wire bounces off another, that bounces off another, and ultimately propagates that energy down the length of the spring. This is what's called a longitudinal wave. And this is a much closer example of how sound propagates through the air. Keep in mind, though, that sound propagates equally in all directions. Okay, so I'm just going to stop it here first. Okay, go back to some of the illustrations. So you can see over here, okay, when you zoom in onto the wave, and let me slow it down. Okay, so you can see over here, the particles within the spring, okay, or the individual coils, they do not move up or down, they instead move left or right. However, because this is a spring and it's fixed on both ends, okay, the whole spring isn't moving along the direction of the wave. What is actually happening is energy is being transferred from left to right, okay, without the spring itself moving left to right. Each of the coils or the particles in this wave, however, they do move left to right, but they do so in a periodic manner. So they return back to their original position after some time and then begin that cycle of motion again. So, like I said earlier, if we look at a single segment of the spring, okay, it's in a periodic motion, and okay, the same thing happens because it's a spring. It's going to transfer some of that motion through the forces to adjacent segments B and C, and so on and so forth until the other end of the spring itself. So the question here posed below by the slides is, do we think that the motion of the segment in the spring and the segment in the rope can be both described as cyclical or periodic? Okay, so the answer is yes, like I explained. For both of these sections inside the medium or parts of the medium, what we are going to see is they do vibrate or oscillate, okay, in a periodic manner back and forth. It's just the direction in which that vibration occurs is going to be different depending on the type of wave and the type of medium. So back to our ripple tank, the demonstration we had earlier, the two videos, okay, you have a shallow glass tank of water, you put it below a wave generator connected to a dipper. So it looks something like this. Okay, so we've got two examples here, just like what I showed you earlier. So that first video was, okay, showing circular ripples. So that wave generator is just a single spherical dipper in the center, going up and down, creating circular ripples. And then the second example is a wave generator that creates a wave in a straight line. So you can see a straight dipper, okay, and you see over here the dotted lines, they are waves traveling in one direction in straight lines. So just now we saw those lines, okay, caused by the refraction of light. And okay, these imaginary lines, they actually join all the adjacent points on the wave that are moving in step. Meaning that, for example, if you go back to the video of the Kallang Wave at the National Stadium, if we draw an imaginary line that connects all the people who were standing up at the same time, okay, that would be that same line. We call that a wave front. So you can observe that the wave fronts, okay, for the different waves that we see, okay, the wave fronts, they are all traveling in the direction of the wave, because there's an imaginary line that shows all the points that are moving in step. So for example, in the wave generator, it is maybe the top of each ripple. They're all in step. Okay, so it's a circular it's an imaginary circle that expands as the wave gets bigger. The Kallang wave, okay, that would be an imaginary line that goes around the stadium as people stand up and then sit back down. So everybody who is standing up, that forms that line. Then it moves on to the next person as the person next to them stands up and they sit down. And then in the wave generator with the flat waves, okay, it is also the same thing. The top of the wave that moves, okay, across the ripple tank. And just now I already mentioned the terms vibration or oscillation. Okay, the motion of any selected point in a wave is periodic, it's repetitive. We call it a vibration or we call it an oscillation, meaning that it's going back and forth. Okay, so all these particles, they are moving back and forth from each other. Okay, so they are always going to be doing that same motion over and over again. That's why we call it periodic and repetitive. So a quick worked example. Okay, small leaf on water surface move up and down as a wave passes. It maintains the same distance from the source of the wave. So this shows that actually waves carry energy but not matter. And then the next one, the small motion of a small segment of a medium is the same whether the wave passes through rope, medium, or spring. So how do we describe this motion? So we can say that the small segment of the medium, or we can say the particle, it oscillates back and forth about a fixed position. Now, the direction in which it oscillates or it vibrates, that, okay, tells us the two different types of waves. In a transverse wave, which is the water waves, as well as the Kallang wave, in our examples, it oscillates in a direction perpendicular to the direction the wave travels in. That means if the wave travels from left to right, the oscillation will be up and down. The individual particles are going to move up and down. For a longitudinal wave, it oscillates in a direction parallel to the direction of the wave travel, meaning that in the spring, okay, as the wave traveled from left to right, the individual loops in the spring or the particles in the spring, they actually travel left and right. So you might also be familiar with sound being a wave, and sound is a longitudinal wave, meaning that, okay, the particles of air, they actually oscillate in the same direction that sound travels. So if you're listening to this, for example, through headphones, okay, what is going to be happening is that the particles of air are going to be vibrating back and forth from the headphones to within your inner ear. And as it does so, okay, the particles bump into each other, and that's how they transmit that energy. But they don't transmit the matter because your ears are not collecting air, for example, right? And how are the particles going to be oscillating? They're going to be oscillating in the direction parallel to the direction of the sound, which means that, okay, right now, if the sound is traveling into your ear, okay, let's say you are, sitting upright, so it's traveling horizontally into your ear. What you're going to see is that the air particles, if you could track them and zoom in, they are going to be oscillating or vibrating left and right. Okay, so that's the end of the first part. We are going to move on to the second part, so that will be the next video.